Welcome to the Deep Dive, your shortcut to being truly well-informed. Today, we're diving deep into something that's, well, really got the developer community buzzing. Apple's recent AI stuff, the core of what they're calling Apple Intelligence. And our mission today really is to get past the big announcements. We want to dig into the actual tech, the architecture, how they train these things, the optimization, all the nuts and bolts behind Apple's new foundation language models. And more importantly, what does this actually mean for you, the developer? What can you do with it?
Exactly. We're basing this mainly on Apple's own tech report, the Apple Intelligence Foundation Language Models Tech Report 2025. It's straight from their machine learning site, machinelearning.apple.com. Super technical, packed with the details we need.
Right.
We'll touch on a 9 to 5 Mac overview too, but yeah, the real meat is in that Apple report. That's where the interesting engineering solutions are.
Okay, so let's jump in. First big challenge.
Yeah.
Getting serious AI actually running on the device, right? In your hand. We're talking about that on-device model, the roughly 3 billion parameter one that runs on Apple Silicon, the one you developers can actually access in your apps. How on earth did they make that work efficiently?
Yeah, it's pretty fascinating how they pulled that off, balancing power with efficiency. Because, performance is just critical for on-device stuff.
Totally.
Their main trick was a really clever split in the architecture, specifically around the key value cache, the KV cache. They basically divided the transformer layers. Block 1 got about 62.5% of the layers, the standard setup.
Okay.
But Block 2, the other 37.5%, they did something different. They actually removed the key and value projections entirely from those layers.
Removed them. Okay, that sounds weird. Wouldn't that hurt performance? What's the benefit there for, for us developers?
That sounds counterintuitive, but it's actually a huge win here. Because Block 2 doesn't have those projections, it can directly share the KV cache generated by Block 1.
Ah, okay. Sharing the cache.
Exactly. And that directly leads to a 37.5% drop in the memory needed for that KD cache, which means for you, the developer, there's just more memory left on the device for your app to do its thing.
Right. Less memory pressure.
Less memory pressure, exactly. And there's another bonus. Because Block 2 isn't calculating its own keys and values, it skips the whole prefill computation step.
Oh, interesting.
Which cuts down the timed first token, the TTFT, by roughly that same 37.5%. So your app feels snappier, the AI results pop up faster. It's smart engineering for on-device constraints.
That is a huge saving on memory and speed. Clever. But that wasn't the only optimization they did for the local model, was it? There was also this quantization-aware training, QAT. Why should developers care about that detail?
Right, QAT. They pushed it really hard for the on-device model, getting it down to just 2 bits per weight.
2 bits, that's tiny.
It's incredibly aggressive.
Oh, yeah.
And that's crucial for keeping the memory footprint tiny and making inference super fast on the user's phone or iPad. Your app just runs smoother. But like you said, 2 bits is tricky territory. Maintaining quality is tough.
Yeah, how did they keep it stable? 2 bits sounds like you'd lose a ton of information, make it really unstable to train.
It's definitely a balancing act. They had to be really meticulous. They used the Atom W optimizer, that's a pretty robust algorithm, plus lower learning rates, gradient scaling, basically ways to keep the training process smooth and prevent it from going off the rails. They also use something called EMA, exponential moving average, on the weights. Think of it like smoothing out noisy data points during training. And critically, they figured out that using a specific balanced set of values for those 2-bit weights, 1.5, -0.5, Mando 0.5, 1.5, made the training much more stable than unbalanced sets.
Ah, the specific values matter.
Massively. So all these little tweaks mean that even though it's radically compressed, the model you use in your app is still fast, efficient, and the quality holds up surprisingly well for the user.
Really impressive what they squeezed out of that on-device model. Okay, but what about the really heavy lifting? The tasks that need more power than even Apple Silicon can manage locally. Let's talk about the server-side models, the ones running in Apple's private cloud compute. How did they build those to be huge, but also, efficient?
Yeah, this is where the scale gets really interesting, and the architecture reflects that. Connecting it back, this allows for that massive compute power, but still feels responsive, like you'd expect from Apple.
Right.
The big innovation here is what they call parallel track, mixture of experts, or PTMO.
Mixture of experts, right. So using specialized submodels.
Exactly. Like having a team of specialists, and you only call the right expert for this specific job instead of everyone weighing in on everything. Saves a ton of computation.
Okay, makes sense. But what about the parallel track part? How does that make it efficient for the cloud?
So instead of one giant sequential stack of layers, they partition the model into several smaller independent tracks. Think of them like parallel processing lanes. Each track handles tokens on its own, and they only need to sync up at certain points, these block boundaries. This cuts way down on the communication overhead between different parts of the model. Like if they use 4 tracks, it reduces that synchronization overhead by something like 87.5%. Huge saving.
Wow, okay.
And within each of these track blocks, they swap out every other regular transformer layer with a mixture of experts layer. But the key is the experts are local to that track. They don't need to talk to the whole system.
Keeping it local reduces bottlenecks?
Precisely. It scales much better and keeps latency super low because you avoid these system-wide traffic jams.
Very clever. And the paper also mentioned interleaving global and local attention. What's the goal there in this big server model?
Yeah, that's another neat trick, mostly for handling really long inputs like long documents or conversations. They alternate layers. Some use local attention looking at a nearby window of about 4,000 tokens using rotational positional embeddings, ROP, which helps understand word order. And then other layers use global attention, but interestingly, without positional embeddings, or no PE. This mix lets the model handle much longer contexts efficiently, avoids weird issues that can pop up with positions in very long sequences, and it also helps keep the KV cache size down, all while maintaining quality.
And compression again, right. Just like the on-device one. The server model uses ASTC adaptive scalable texture compression down to about 3.5 bits per weight. What's special about ASTC here?
ASTC is cool because it actually comes from the world of GPU graphics compression.
Oh, really? Graphics.
Yeah, and Apple leverages the fact that their GPUs already have dedicated hardware to decompress ASTC really, really fast. Like essentially zero compute cost from the GPU's main cores.
Hardware acceleration.
Exactly. So the weights are stored compressed, saving memory bandwidth and storage, but they get decompressed on the fly without adding any latency to the AI's response time, which is obviously critical for a responsive cloud service at scale. It's a neat hardware-software synergy.
Okay, let's shift a bit to the foundations, the stuff both models share. Data, languages, vision. Apple makes a big deal about their responsible AI approach. What does that actually look like in terms of where they get their data, especially user privacy?
Yeah, they're very clear on this. They emphasize diverse, high-quality data, but also protecting privacy. They explicitly state they do not use your private personal data or your interactions with apps to train these foundation models. That's a key point.
Okay, that's good to hear. So where does the data come from then?
It's basically 3 pillars. First, public web data crawled by Applebot. They mention using advanced techniques like headless rendering so they can see pages like a real browser does, with JavaScript and all, and using models to filter that data for quality. Then they respect robots.txt, of course.
Standard web crawling stuff, but refined. Okay.
Second, licensed data. They mention licensing content from some publishers, which gives them access to curated, likely higher quality material. And third, which is maybe more interesting, synthetic data. They actually generate a lot of data using smaller models and specific pipelines, especially for things like math problems, code generation, instruction following, and vision language tasks. This synthetic data seems really important for fine-tuning and also boosting multilingual capabilities.
Interesting. So they're creating data to fill gaps. And speaking of multilingual, that was a big push, wasn't it? Making these models work well globally. What did they do there?
A huge push. They increased the proportion of multilingual data in their training mix from about 8% to 30%. That's a massive jump, like 275% more non-English data.
Wow.
Some of that is naturally diverse web content. Some is targeted synthetic data generation. And alongside that, they expanded the vocabulary. The model understands the tokenizer by 50%. Went from 100,000 tokens up to 150,000.
And why does that larger vocabulary matter?
It just allows for a better, more efficient representation of words and phrases across many different languages, especially those with complex scripts or characters. It means the model isn't struggling to piece together common words in other languages using awkward combinations of basic tokens.
So, okay, putting it together for the developer listening, what does this improved multilingual support actually mean when building an app?
It means things like the built-in writing tools, summarizing, rewriting, proofreading, should just work much better and more naturally in all the languages Apple supports. For you, it means you can build apps with sophisticated language features that feel truly native to users in, say, France or Japan, without you needing to find or train separate language models. It broadens the reach and quality of AI features in global apps.
Makes sense. Okay, beyond text, there's the whole visual side. Apple Intelligence understands images too. How do they bake that in? What's going on under the hood for vision?
Right, the vision part. They have a dedicated vision encoder. Think of it as the AI's eyes. It takes an image and extracts meaningful features. This encoder has two main parts: a vision backbone that does the initial heavy lifting of seeing the image,
Okay.
and then a vision language adaptation module that translates those visual features into a format the language model can understand, basically turning pictures into image tokens.
And are these components the same for the on-device and server models?
Similar concept, but different sizes for efficiency. The server model uses a big VITG backbone, about a billion parameters, for top accuracy. The on-device model uses a leaner VT-L backbone, around 300 million parameters, optimized for running locally without killing the battery.
Got it. And the data they used to train this vision part must have been massive.
Oh yeah, over 10 billion image-text pairs crawled from the web. Plus another 5 billion synthetic image caption pairs, probably to get richer descriptions. They also included text-heavy images, think PDFs, charts, flyers, using OCR so the model learns to actually read text within images.
Ah, reading text and images, that's useful.
Definitely. And they added high-quality, domain-specific data, too, for areas like science and healthcare. It's a really diverse visual diet.
And how does this impact developers practically? Like dealing with different image sizes or resolutions?
That's a good point. During the fine-tuning stage, they actually trained the system to handle high-resolution images, up to 1344 by 1344 pixels, often by tiling them. This helps it understand fine details and read small text accurately.
Okay.
But for the on-device model, you actually get choices. There's a high-res mode for detail, a balanced mode, and even a rapid mode that uses smaller 224 by 224 images when you only need a general understanding of the picture. And speed is critical.
So developers can trade off latency for detail.
Exactly. It gives you flexibility depending on your app's needs. So, thinking about this, how could you leverage this kind of visual understanding? What new app features could you build that combine language and vision in interesting ways?
Yeah, lots to think about there. Which leads us right into the developer framework itself, the foundation models framework. Apple's gateway for us developers. They're pitching it as making generative AI easy, like a few lines of code, often free for on-device stuff. How does it actually work? How do we tap into this power?
The core idea is making it super Swift native and, crucially, type safe. The star feature, I think, is guided generation.
Guided generation, okay.
Imagine instead of asking the AI for text and then trying to parse it, you just define a Swift struct or enum for the data you want back. You put an @generable annotation on it.
Just an annotation.
Just an annotation. The Swift compiler and framework handle the rest. They translate your Swift structure into a format specification, inject that into the prompt behind the scenes, and the model, which has been trained to understand these specs, generates output that perfectly matches your structure.
Wow.
And OS Gaiman helps ensure it follows the rules using constrained decoding, and the framework hands you back a fully formed, ready-to-use Swift object. No parsing strings, no dealing with badly formatted JSON.
Okay, that gets rid of a massive headache for developers. Like, probably the biggest pain point with using LLMs and apps is handling the output reliably.
Exactly. It massively simplifies things. It makes the whole integration way more robust. And tool calling builds right on top of this. You define tools your app can perform using a tool Swift protocol. Again, because it uses guided generation, the framework guarantees the tool calls are structurally correct. No made-up tool names or wrong argument types.
Nice.
It even manages complex sequences of tool calls, like parallel or serial ones, automatically. So you can easily let the AI use your app's specific functions or data safely.
And managing the conversation state, they have something called language model session.
Right. That's designed to make conversation smooth. It's an append-only session tied to the model's key cache. This link prevents the cache from being accidentally wiped, which keeps follow-up responses really fast.
Okay, maintains context efficiently.
Yeah, and it supports streaming. So
it sounds incredibly well thought out from a developer experience perspective. So the question for you listening is, how are you going to use these type-safe, robust features? What kind of intelligent experiences can you build now that maybe seemed too flaky or complex before?
Yeah, it really lowers the barrier to entry for building reliable AI features.
All right, let's quickly look under the hood one last time. The training process itself, how they evaluate these things, and this whole responsible AI angle woven through it. What was the training recipe like?
Well, the engineering effort is pretty staggering, honestly, especially how they focused on efficiency. For pre-training the on-device model, they started with a dense model trained on like 14 trillion tokens. Massive amount.
Trillion, okay.
But then they did this clever thing called sparse upcycling to turn it into a mixture of experts model temporarily. Then they used that bigger MOE model to distill knowledge back down into the final dense model, retraining the last 10% of tokens.
Why do that complicated dance?
Get this. That whole process cut the training cost for the large teacher model by 90%. 90.
Hmm.
While actually boosting the final model's performance, that's a huge engineering win. A
Yeah.
real game changer for making large model training more feasible.
Incredible. 90% cost reduction and better performance.
Oh, okay, so after that base pre-training.
They did more stages of continued pre-training to boost specific skills, more math, more code, better general knowledge, expanding that multilingual data significantly, adding the multimodal vision capabilities, and importantly, context-lengthening training on sequences up to 65,000 tokens.
So it can handle really long inputs.
Exactly. Think entire documents, long chat histories, much more coherent over long stretches.
And then the final polish, the fine-tuning and reinforcement learning.
Yep. Supervised fine-tuning, SFT, used a mix of human examples and synthetic data. Big focus on vision, reasoning, reading text and images, multilingual OCR, and grounding, making sure responses are factually based.
And for the reinforcement learning from human feedback, RLHF, they used a method called RLOO with a distributed asynchronous setup. Basically, a sophisticated way to efficiently train the model based on human preferences and various reward signals, including from image interactions, to make it helpful, harmless, and honest. That's where a lot of the safety and desired behavior gets baked in.
So all that training, how do they actually perform? You mentioned benchmarks like MMLU.
Yeah, on benchmarks, the on-device model holds its own pretty well against similar-sized open models like Qwen or Gemma. Sometimes leads, sometimes lags slightly, depending on the specific test.
Okay.
The server model is also very competitive against things like Llama 4 Scout, strong across the board. Obviously, the giant frontier models like GPT-4o or the biggest Qwen models still pull ahead in raw scores, as you'd expect.
Makes sense.
But it's crucial to see the optimization impact. Like, adding QAT to the on-device model dipped its MMLU score slightly, from 67.8 to 64.4. That's the deliberate trade-off they made for that massive on-device efficiency gain. Human evaluations also generally showed good results, confirming they work well in practice.
And wrapping up with responsible AI. We touched on data privacy, but how else is it integrated? What does it mean for developers day to day?
It's really meant to be foundational. Those principles empower users, represent users, design with care, protect privacy. They guide things like data filtering, building that detailed safety taxonomy to catch harmful content across 58 subcategories.
58.
Yeah, it's detailed. And importantly, doing this multilingually, not just for English. Safety needs to work everywhere.
So what does this all mean for you, the developer?
It means you're building on a platform that takes this stuff seriously from the start. A lot of the safety guardrails are built into the framework itself, helping mitigate problematic inputs and outputs automatically. This reduces some of the burden on you.
That's a big plus.
Definitely. Plus, user feedback loops, like the thumbs up down in Image Playground or the general feedback assistant, feedback into the system to help Apple continuously improve safety and quality. So you're essentially leveraging a system designed with ethical considerations and privacy baked in, which hopefully helps build user trust in the AI features you create.
What a fascinating look at the tech behind Apple Intelligence. We've covered the clever architecture for efficiency, KV cache sharing, PTMoE. We've seen the focus on data quality, privacy, multilingual support, and vision. And critically for you developers, the power and simplicity promised by the foundation model's framework with things like guided generation and type safety in Swift.
Yeah, the transparency in their tech report is really commendable. It shows the sheer depth of engineering, the trade-offs they made for practical deployment, the multi-stage training, and how responsible AI isn't just an afterthought. These models seem built to be powerful but also reliable tools for developers.
So the final thought for you, the developer listening, you've now got these incredibly sophisticated models, these robust type-safe tools right there in Xcode, often running for free on the device. What completely new kinds of app experiences, things that seemed impossible or just too unreliable before, can you start building now? What problems will you tackle with this new level of intelligence readily?